Hello, everybody. So what have we done so far in polynomial time? We defined how to measure time. We talked about various time complexities, most importantly, polynomial time. We discussed time hierarchy, more time means more power. And then we looked into NP, which is the class of problems that can be solved in non-deterministic polynomial time, decided in non-deterministic polynomial time. We discussed NP completeness. We showed that there are many problems that are NP complete, first by the Cook-Levin theorem and then using polynomial time reductions. And in the next, in this video and the next two, we're going to go beyond P, beyond NP, and we're going to have a steadily growing picture here with more and more classes and more specific problems in them. And hopefully the picture will continue to be clear to you. So today we're going to talk about co-NP. And the definition of co-NP, like every co-class, is all their languages such that their complement is in NP, in this class. So co-NP is all the L's such that not L is in NP. But we can also think about it directly and ask, how does a co-NP computation look like? It again, like an NP computation, you have many paths because we are looking at the complement of an NP machine. It can make many guesses. But a co-NP says that for this X, none of these paths lead to accept. So we can think about it as all of the paths lead to non-accept. And this gives us this ability to ask for all question. If NP is an there exists question, does there exist an accepting path? Here we have that for all paths, there are not accepting. So in NP algorithm, we can guess and use it in our pseudocode, guess a string of some polynomial length, and the machine accepts if there is some guess that leads to an accept state. In co-NP algorithm, we can try all. Instead of guessing the one good one, we can try all. So try all strings of x to the k length and see something about them. So, and the machine accepts if every y leads to an accept state, which is just the same as a reject state. So this is a way I want you to be able to think about co-NP. It is for all rather than exist. But we can always fall down to just looking at the complement of a language and checking that it is in NP. So tautology is the set of Boolean formulas that every variable assignment satisfies this formula. So tautology are formulas that are always true. They are a tautology. Theorem is that tautology is in co-NP. How would you write a pseudocode for a co-NP machine that decides tautology? To do that, you would say for all, try all assignments and check that none of them, that all of them are satisfying. How would you write tautology as the complement of some NP language? This is the other way of doing it. What's the complement of tautology? So if we assume that every string corresponds to some formula, which we can, and then the complement of tautologies are formulas that have some unsatisfying assignment. And this is in NP because you can guess an assignment and check that it is not satisfying. So let's ask some questions. Is P is a subset of coin P? Yes. Just like P is contained in NP, you can see it in two ways. P is closed under complement, so P is contained in NP, and therefore its complement, which is also P, is contained in coNP. Another way is just to say that this is a trivial coNP pseudocode that doesn't have any try-all. And so, yeah, to prove it formally, L is in NP implies that not L is in P, and hence not L is in NP, and therefore therefore L is also in coNP. General deterministic complexity classes are closed under complement. So P is closed under complement. Is NP equals coNP? Think about it. This is open. We do believe that NP is different than coNP, but we don't know how to do it. If NP equals coNP, then you can somehow do the for all with there exist. And in particular, think about an NP problem. SAT, a coNP equivalent is that there is no satisfying assignment. NP means that you can have a proof. There is a simple proof that that the formula has a satisfying assignment, which is just a satisfying assignment. If NP equals coNP, then it means that there is a simple short proof that there is no satisfying assignment. And it's hard to think how you would prove it. So it talks about all assignments being non-satisfying. It's just an intuition. It can be absolutely false because we don't know if NP equals coNP or not. So it is believed that NP is different than coNP. Right, so we have P, NP, and coNP, and we don't know exactly what happens in all of those. So we have NP completeness. We also have coNP completeness. So a language B is coNP complete if it is in coNP. And for every other language in coNP, there is a polynomial time reduction to B. So from every A in coNP, A reduces in polynomial time to B. This is just the analog of NP completeness. NP completeness is that you need to be in an NP and you are NP hard. CoNP completeness is that you are in CoNP and you're CoNP hard. So let's look at another language, ansat. Phi is a Boolean formula and no variable assignment satisfies phi. Theorem is that ansat is CoNP complete. Ansat is in CoNP because its complement is sat and it is in NP. Otherwise, you can also think about the pseudocode, try all variable assignments and check that all of them fail to satisfy phi. But the complement works. So now we want to also prove that ansat is CoNP hard. How would we do that? You can think about it. Well, let A be any language in CoNP. We want to show that it reduces in polynomial time to ansat. And in fact, we know that already because the complement of A reduces to the complement of ansat. So on input W, transform W into a formula phi, just using the Cook-Levin theorem that reduces not A to sat. So you have, because not A is in NP, you have a non-deterministic machine N for not A, and then you can transform it using the Cook-Levin theorem into a formula phi. W is in not A means that phi is sat, and W is not in not A means that phi is not sat. Right? This is just because we have a reduction from not A to sat. And I want to claim that this is also a reduction from A to ansat. And we already discussed it when we talked about reductions, just mapping reductions, and it's the same for polynomial time reductions. A reduction from A to B is also a reduction from not A to not B. It's the same reduction, is also a reduction from not A to not B. And seeing it here, one thing is W is not in not A means that W is in A, means that phi is not in sat, which means that phi is in ansat. And W is not in A means that phi is not in ansat. So this is a reduction from A to ansat. In general, every reduction from a language A to a language B is a reduction from not A to not B. Let's think about tautology again. So phi is a Boolean formula that every variable assignment satisfies phi. And this is the same as phi is such that not phi is in ansat. If every assignment satisfies phi, then no assignment satisfies not phi. Therefore, tautology is coNP complete as well. Why? Tautology is in coNP, we already shown it before. And tautology is coNP hard. And the reduction is from ansat. Ansat reduces in polynomial time to tautology. So given the formula phi, you just output not phi, because phi is in tautology if and only if not phi is ansat. So we can use exactly the same kind of structure of reductions to look at more and more problems that are coNP complete. Alternatively, we can look at every problem that is NP complete and see that its complement is coNP complete. So every NP complete problem has a coNP complete counterpart. So, and that's just for the reason we discussed before, because the reduction from every A to this NP complete problem is just a reduction from not A to the coNP complete problem. So NP complete problems are SAT, 3-SAT, click, vertex cover, subset sum, and the coNP problems that are equivalent is ansat, tautology, non-click, so there is no click of some size, etc., etc. So we have P, NP, coNP. What about the intersection? What about the NP intersection coNP? So if P equals NP intersection coNP, you can think about it for a second. Well, this is again open. I would just say that at least for a while, we have based a lot of our economy on the assumption that P is different than NP intersect coNP, and without knowing it. So I didn't see in economic journals any worried articles about what happens if P equals NP intersect coNP, but they should have. And the reason is that there is an interesting problem in NP intersect coNP, and it is factoring. There are other problems that relate to cryptography. In fact, there are not a lot of problems in NP intersect coNP that we care about, and many of them are related to cryptography. As a side note, that wouldn't make sense to anybody who didn't study cryptography. every problem on which you can base one-way permutations corresponds to a problem in NP intersect CoNP. If you don't know about cryptography, erase what I said now and ignore it. It will play no part in our class. What is factoring? You can present it in different ways, but as a decision problem, you can look at m comma n, where n is smaller than m and larger than 1. There are integers such that there is a prime factor p of m, with p being at least n and smaller than m. So this just means that m is a composite that you can factor. If factoring is in P, then we could break many public key cryptography that we currently use. In fact, if we believe in the common model for quantum computation, then factoring can be broken once we will have quantum computers that are large enough, which, I mean, this was known for decades now, and it finally seems like the construction of quantum computers is catching up, but we're still a way to go. But it was known that in this model, it is possible quantum computers can factor numbers in polynomial time, meaning that they can break these public key cryptography systems. And therefore, there is a large movement within cryptography known as post-quantum cryptography to replace these public key systems with other systems that are currently not known to be broken by quantum computers that we currently don't know how to build. But we are thinking ahead and it's important, so power to the people. But still, and in fact, there are people that believe that factoring itself is not hard, that you can actually factor even by classic machine. We don't know how to do it, and for a long time there was an incentive to do that, so the confidence have been reduced in this statement. So as a recap, factoring is a problem that we currently don't know that it is in P, and we base on this assumption that factoring is not in P a lot of our cryptography. The theorem that we want to show is that factoring is in NP intersection CoNP, which in particular will indicate that unless NP equals CoNP, it is not NP hard. And in fact, much of cryptography, we don't know how to base cryptography on NP hard problems, and that's an interesting question on its own. Now, how can we show that factoring is in NP intersect CoNP? As you can think, factoring is easily in NP because I can just give you the factors. So I can just give you P, and it will prove that Mn is in factoring. The part that it is in CoNP is harder and a bit non-trivial. And in fact, I'll argue it using a less trivial theorem, a theorem that we knew much later. So it's kind of anachronistic or silly because I'm going to prove a theorem that's non-trivial but not as hard, that factoring is in NP intersect CoNP, using a theorem that is pretty hard and wasn't known for a while, that primes is in P. So what are primes? Primes are all the numbers that are primes, prime integers. This problem, for a long time, we knew lots of algorithms of various sorts that were almost polynomial time algorithms or randomized algorithms that ran in polynomial time, but we didn't know a deterministic algorithm that ran in polynomial time. In a breakthrough result in 2004, it was shown how to do probability in deterministic polynomial time. In fact, this was done by de-randomization of a randomized algorithm that ran in polynomial time. I'll talk about de-randomization a bit in one of the following videos. But that was definitely a breakthrough result, although we knew or expected and all believe that it is true, giving it and giving the proof, giving the algorithm was a breakthrough. So using that, we're going to show that factoring is in NP intersect co-NP, a fact that, as I said, was known way before we knew that primes are in P. So factoring is in NP intersect co-NP. And the proof is that the prime factorization of M can be used to prove both that Mn is in factoring, or if it's not, that to prove that Mn is not in factoring. So if I give you the prime factorization, the unique prime factorization of M, you know in particular which are all the prime factors, and you know that whether any of them is between N and M. So in a sense, what I want to say is that this prime factorization is a guess that that demonstrate that factoring is in NP, but also demonstrate that not factoring is in NP, meaning that factoring is in co-NP. Therefore, factoring is in NP intersect co-NP. Now, how can I verify that the prime factorization is correct? That's easy. I just verify that each one of the PIs is prime, and this I do because primes are in P. And then I take this product and check that it is M. So if there is a PI that's larger than N, then Mn is in factoring, otherwise it is not in factoring. So this is a certificate both for factoring and for not factoring. Therefore, both factoring and not factoring are in NP, meaning that factoring is in NP intersect co-NP. So what do we have? We have P, we have NP, we have co-NP, we have SAT, which is NP complete, and many other NP complete problems. We have tautology and many other co-NP complete problems. We have a few interesting problems within NP intersect co-NP, like factoring. So we have NP complete problems, SAT, 3-SAT, click. We have co-NP complete problem like ansat, tautology, non-Hamiltonian path. And we don't have NP intersect co-NP complete problems. We don't know if they exist. We don't know if there is a problem that it is as hard as any other problem in NP intersect co-NP. And for this reason, we know less about NP intersect co-NP. This is what I hinted some videos ago, that for classes that we don't have complete problems, we know less about. So we know a lot about NP, a lot about co-NP, much less about NP intersect co-NP. The reason that we don't know an NP complete problem is that P, NP, and co-NP are defined in terms of a specific machine model, deterministic machine, non-deterministic machine, co-non-deterministic machines, and we somehow create at least the first complete problem by encoding these machines. NP intersect co-NP is not known to have a corresponding machine model. It is the intersection of two languages that are defined through a machine model, but there isn't a NP intersect CoNP computation. So we explained what is an NP computation, what is a P computation, what is a CoNP computation. We don't know how to define what is an NP intersect CoNP computation, and that makes it harder to come up with a complete problem. Of course, if P equals NP, then P, NP, and CoNP are all P, and therefore their intersection is all P and everything is easy. But otherwise, we would really love to have also an NP intersect CoNP complete problem. So to complete this discussion, NP as short proofs. We define CoNP that a priori do not look like they have a short proof. And indeed, if CoNP will have short proofs that are easy to verify, then we'll have that NP is equal to CoNP, which we don't expect to be true. But I will discuss a different kind of proofs that do apply to CoNP and even way beyond. And what we'll discuss in the next two videos is what happens, what exists beyond NP and CoNP. Thank you.